Welcome back to the Deep Dive, where we unpack the most groundbreaking ideas in AI, giving you that shortcut to being genuinely well informed. This is a really crucial part of our Beyond Transformer series. We've been systematically charting the course, exploring these incredible advancements in sequence models that are pushing past the standard transformer architecture. We've looked at the rise of state space models, SSMs, from their theoretical roots right up to Mamba and Hydra. Today, we're diving deep into a framework that's, well, not just technically fascinating, but also deeply practical in bridging these architectural divides. We're talking about MOHAWK.
Yeah, and it tackles a really interesting dilemma we're facing in AI right now. I mean, transformers, they've completely reshaped the landscape, especially with LLMs, right? Setting new benchmarks. But they have this fundamental limitation, that quadratic scaling with sequence length. Put simply, you double the input length, the compute and memory needs quadruple. And that's a massive hurdle, particularly for, really long contexts like analyzing a whole book or complex legal documents, or even just for efficient inference, where speed and low resource use are key.
Right, and on the other side.
Well, on the other side, you've got models like Mamba, built on SSMs. They offer this amazing linear scaling, double the input, double the cost, super efficient for long sequences. But, and this is the catch we've discussed, building these SSMs from scratch to match, say, a big pre-trained transformer, that takes just immense, often totally impractical computational resources. You're essentially starting from zero against models that have learned over trillions of tokens.
So it's this kind of catch-22 situation. Powerful transformers that get too expensive and efficient SSMs that are too expensive to train up to that same level from nothing. Feels like we're stuck.
Exactly.
And this is precisely where MOHAWK comes in. It's this groundbreaking multi-stage framework designed to tackle exactly that problem. Its core mission is, well, pretty ingenious, actually. It tries to leverage all that intelligence already baked into those huge pre-trained transformers, all that knowledge they gain from years of training and billions in compute spend, and it aims to efficiently transfer that knowledge over to the more agile, subquadratic SSMs. It's about finding a smart shortcut, not just rebuilding everything.
And connecting that to the bigger picture, what MOHAWK enables is genuinely transformative for the field. It allows for the creation of models like Phi-Mamba and Hybrid Phi-Mamba. These aren't just small tweaks. They hit state-of-the-art performance on par with much larger or way more expensively trained models. But, and this is the crucial part, they do it with significantly less new training data than you'd normally need. The research is pretty clear on this. It's not just a slight improvement. It's demonstrably, quote, far more effective than conventional distillation techniques.
Can you unpack that a bit? How does it differ from conventional distillation?
Sure. Conventional distillation often works by, just getting a smaller student model to mimic the final outputs, the answers, of a larger teacher. But if the student's internal architecture, its whole way of processing information is fundamentally different, that mimicry can only get you so far. It's skin deep. MOHAWK, though, it's more like teaching someone a new language by first aligning the basic grammar, then the underlying concepts, then practicing conversation. It's this deep layered transfer that makes it work so much better, especially when languages, the transformer and SSM architectures are so different fundamentally.
So it's not just about matching answers, it's about aligning the thinking process itself.
Precisely. It's aligning the process, even with different underlying machinery. And that raises the key question, right? How do you actually transfer intelligence so effectively between architectures that seem so different? One like a database, the other like a constantly updating summary.
And that's exactly what we're going to unpack in this deep dive. We'll break down MOHAWK's innovative three-stage process step by step. We'll delve into the principles behind it, including some really fascinating mathematical links between these architectures. And finally, we'll look at the hard results, the compelling, quantifiable data that shows its power and how it really delivers the best of both worlds. Top-tier performance with impressive efficiency. So let's get into it.
Okay, we've set the scene for MOHAWK's ambitious goal, bridging these two really distinct architectural worlds. Before we jump into MOHAWK's stages, maybe let's quickly revisit why SSMs and Mamba specifically are such an exciting direction, especially when you contrast them with transformers. It gets to the heart of how they fundamentally operate.
Yeah, absolutely. SSMs, they're characterized by this state that constantly compresses history. Think of it like they operate in this online streaming fashion, maybe like a seasoned journalist at a live event. They're taking in new information constantly, listening to everything, but instead of writing it all down verbatim, they're distilling it into this concise, evolving understanding, updating their state on the fly.
Okay, so constantly summarizing. How does that compare to transformers?
It's fundamentally different. Transformers, by their nature, cache every element of their history. They act more like, say, a meticulous court transcriber, recording every single word just in case it needs to be recalled precisely later. They store it all explicitly.
Yeah.
And this difference, compression versus explicit caching, is really key to understanding their strengths and weaknesses. One prioritizes efficiency and agile summarization. The other prioritizes perfect recall, but with that quadratic cost baggage.
That journalist versus court transcriber analogy really helps make it concrete. So transformers are great at pulling specific details from their huge database, but that database gets unwieldy, quadratically so, for really long inputs. SSMs, meanwhile, are efficient summarizers, but maybe traditionally struggled with that exact, precise recall.
That's generally the trade-off, yes. And brings us right to the core challenge MOHAWK is designed to solve, the difficulty of this cross-architectural transfer. It's not just about making a big model smaller, it's about transferring learned representations and, crucially, inductive biases between these fundamentally different ways of processing information. Imagine trying to teach that journalist to think like the court transcriber at a fundamental level, or vice versa. It's a really deep conceptual shift.
And this challenge gets even more interesting when you think about the types of data they handle best, right?
It's exactly. Transformers, as we've discussed before, really shine on pre-compressed data. Tokens, basically, breaking down text into meaningful chunks. But the performance can actually drop relative to SSMs when you feed them raw, high-resolution stuff like individual characters, raw audio, or long DNA sequences, even if you give the transformer way more compute power. And that's because, as some research points out, attention, while powerful, can be a poor inductive bias for that kind of raw, continuous data.
Inductive bias meaning, like, it's built-in assumption about the data.
Yeah, precisely. It's the model's inherent preference or assumption. For SSMs, particularly Mamba, that bias is towards efficient compression and capturing long-range patterns in a streaming way. They're sort of inherently built to distill these long, continuous streams into a compact state. That gives them a clear advantage for directly processing raw data, where compression is really the name of the game.
Okay, so this sets up MOHAWK's approach, which you called its unconventional wisdom. Most distillation just matches the final answers.
Right, getting the student to parrot the teacher.
But MOHAWK goes deeper. It's aiming for alignment beyond just the outputs, digging into the internal workings, the learned representations of these very different model families. It's not just about getting the same result. It's about getting the student to process information in a way that's analogous to the teacher, internalizing its logic, even with different computational guts, like translating the teacher's understanding into the student's native cognitive language, not just copying its words.
Which, makes you wonder, if the architectures are so different, how do you even start aligning their internal representations without just forcing something that doesn't fit? That's the puzzle MOHAWK really tackles.
And that brings us perfectly to stage 1 of MOHAWK matrix orientation. This is the foundation, maybe the conceptual Rosetta Stone, for achieving that deeper alignment we were just talking about.
Exactly. The goal here is to align the representation spaces. So think of the complex, high-dimensional patterns the networks learn internally. We want to align those patterns between the teacher specifically, the pre-trained transformers attention matrices, and the student, the SSM, particularly Mamba's mixer components. It's about getting the internal language of the SSM's processing to be analogous to the internal language of the transformer's attention, finding common ground in how they represent relationships in the input.
And how does it actually do that? What's the mechanism?
Well, it involves matching the attention matrices from the transformer to the matrix representations of the SSM's mixing layers. Now, this is a bit more nuanced than typical distillation. Some older work did try similar attention matrix matching, but MOHAWK's approach is distinct. Instead of using, say, a softmax-based attention loss focused on probability distributions, it uses a different loss function, one that's not based on softmax. And this loss function specifically optimizes for aligning the structural properties of these matrices. It's not just part of some big end-to-end goal focused on the final output. This targeted alignment allows for a much more precise calibration of the student's internal structure against the teacher's, focusing just on making their internal relational understanding similar, separate from the task objective itself, at least initially.
Okay, so it's a very focused structural alignment first.
Right. And this structural compatibility, it isn't just a handy trick. It actually has some deep theoretical backing. There's this paper, Transformers or SSMs, from the same authors, actually, which shows a really profound link. It shows that SSMs, especially selective ones like Mamba, can be represented mathematically as something called semi-separable matrices. Without getting too deep into the math, A semi-separable matrix is basically a special type of matrix where its structure allows for very efficient computation and storage. It has this particular kind of dependency structure.
Okay, so there's an underlying mathematical structure.
A very specific, efficient one. And even more interestingly, the paper shows that naively computing a scalar-structured SSM is actually equivalent to quadratic masked kernel attention. So this structural duality, it means that even though they look different on the surface, one processing recurrently, the other using attention, there's this fundamental mathematical common ground. It's like finding out two different musical instruments are based on the same underlying physics of sound waves. This provides the deep reason why this kind of cross-architectural alignment is actually feasible and effective. MOHAWK cleverly exploits this shared mathematical structure.
Wow, okay. That's pretty profound. And they actually quantified this compatibility.
They did. And this is where it gets really compelling, moving from theory to hard numbers. Table 6 in the MOHAWK paper measures the distance or dissimilarity between different matrix families and the standard self-attention matrix mixer. And the results are striking. The SSM matrix family, the math behind Mamba, provides the closest approximation to the self-attention matrix mixer. What's more, the Mamba 2 mixer family, which is an SSD, structured state-space duality model, kind of an evolution of Mamba, is only about twice the distance. Compare that to linear attention, another attempt at efficient attention, which is 3 times the distance.
So the data really backs up this inherent closeness between SSMs and attention, mathematically speaking.
Exactly. It's concrete, quantifiable evidence. Stage 1 isn't just a hopeful guess. It's built on understanding these deep architectural connections, finding the closest relative in the architectural zoo, so to speak.
Okay, so stage 1 establishes this fundamental mathematical common language through matrix orientation. What comes next? Once they're speaking the same language, how do you transfer the actual knowledge?
That leads us right into stage 2. Hidden state alignment. Now we move beyond just matching the abstract matrix structures. Here, the focus is on directly transferring the rich, learned representations themselves, you could almost say the thoughts of the teacher model.
The hidden states, you mean, the internal outputs of each layer.
Precisely. As a model processes information, each layer produces more abstract, refined representation that's its hidden state for that layer. Stage 2 aims to directly align these hidden states between the corresponding blocks of the teacher transformer and the student SSM. This direct alignment is crucial because it helps ensure the student isn't just mimicking the teacher's final answer, but is actually absorbing its deep patterns of processing information along the way. It's like making sure a student doesn't just memorize formulas, but actually understands the reasoning at each step of solving a complex problem.
And you mentioned this is implemented as a distinct phase in a MOHAWK. That seems important.
Yes, very. It sets it apart from some other distillation methods that might try to bundle this alignment into one big end-to-end objective. By isolating this phase, MOHAWK gives more precise control over transferring that intermediate knowledge. It makes sure the student really internalizes the teacher's representations layer by layer. Isolating it also kind of prevents the final task objective from interfering too early, letting the student build a solid internal understanding first before optimizing for the final answer. It's a more progressive learning strategy.
That makes sense. Build the foundation, then refine. What's the practical impact of doing it this way? Is there evidence it works better?
There is, and it's quite interesting. This hidden state alignment seems to have a compounding effect on knowledge transfer, building on that structural alignment from stage 1. Think of it as refining the student's internal thought process block by block. And the empirical results in Table 3 of the paper are really telling here. They compare different distillation setups. If you only use the final stage, stage 3, which we'll get to models that are already structurally closer to the transformer, like maybe hybrids with some attention layers, naturally benefit more. They already have some similarity.
Okay, that seems intuitive.
But, and this is the really cool part, when you combine stage 2, the hidden state alignment, with stage 3, models that are less similar to the teacher, like a pure Mamba model, show even more significant performance improvements. This strongly suggests that stage 2 is absolutely crucial for bridging that architectural gap for diverse student models. It allows even structurally different students, like Mamba, to truly internalize the transformer's complex reasoning, not just superficially copy it.
Got it. So stage 1 aligns the fundamental math. Stage 2 aligns the internal step-by-step processing, the hidden states, making sure they understand concepts similarly. With that deep internal alignment established, it feels like we're ready for the final step, the part that ties it all together for the final output. What is stage 3?
Stage 3 is weight transfer and knowledge distillation. This is the grand finale, bringing everything together. At its core, it uses a pretty standard technique, end-to-end distillation of the teacher model's logits. Just quickly, logits are the raw, unnormalized scores a network produces before they get turned into probabilities. Think of them as the model's raw confidence scores for each possible output. Distilling these logits means the student learns to match not just the teacher's final prediction, but the whole distribution of its confidence across all options. It's a richer learning signal than just matching the final probability.
Okay, so standard logit distillation. But what makes it powerful here?
What makes it powerful in MOHAWK is that it builds directly on the deep alignments achieved in stages 1 and 2. That prior alignment makes this final stage much more effective. It allows for the joint fine-tuning of all the students' components simultaneously because they're already speaking the same language internally. You're not trying to force a badly misaligned model to learn everything at once. It's the final step, ensuring the student, now well-aligned internally, also produces outputs that closely mirror the teacher's high-quality predictions.
And the results bear this out. This stage is necessary for top performance.
Absolutely critical. Table 3 in the paper shows this very clearly. All the tested architectures, the pure Mamba, the hybrid Mamba attention models, they only achieve their highest scores after this final end-to-end alignment stage. The paper explicitly says this multi-stage process is demonstrably far more effective than conventional distillation techniques. It's not just marginal gains. It shows that by progressively aligning structurally, then representationally, then at the output level, MOHAWK unlocks performance that simpler methods just can't reach. It's like that perfectly choreographed dance. Each stage builds on the last for a synchronized result.
Makes sense. It's a holistic approach.
And just a practical note on the implementation detail for the final Phi-Mamba model, they actually reduced the learning rate specifically for this stage 3. This is pretty common in deep learning, especially during fine-tuning. A lower learning rate helps stabilize training when you're trying to refine an already well-aligned model, preventing wild oscillations and helping it converge smoothly to the best solution. They use the AtomW optimizer, specific beta values, weight decay to fight overfitting, gradient clipping for stability, and that warm-up stable decay scheduler we mentioned earlier. This level of careful tuning across all stages really underscores the engineering rigor that went into making MOHAWK work so well in practice.
Okay, so we've journeyed through MOHAWK's 3 stages: matrix orientation, hidden state alignment, and finally weight transfer and knowledge distillation. A really sophisticated process. Now let's talk about the payoff. The actual models born from this framework, Phi-Mamba and Hybrid Phi-Mamba. These are the concrete results that show it works.
Exactly, and the results are impressive. These models achieve state-of-the-art performance across a whole battery of tough downstream tasks: language understanding, common sense reasoning. We're talking benchmarks like Wino Grande for pronoun resolution, HelloSwag for plausible passage endings, PIQA for physical common sense, ARC Challenge and Easy for science questions, and Lambda for predicting final words requiring long context. Tables 1 and 2 in the paper lay out the scores, showing them competing strongly with or even beating established models in their size class, even ones trained much more extensively.
Right, and that brings up the really crucial point. It's not just that they perform well, it's how efficiently they got there. The key takeaway here is achieving that state-of-the-art performance with drastically less training data compared to training from scratch. You mentioned the Mamba 1.5b model was distilled using just 5 billion tokens.
That's right, only 5 billion tokens.
I mean, compare that to the hundreds of billions, even trillions of tokens used for training large transformers like GPT-3. It's a tiny fraction. That represents a huge saving in compute cost, energy, carbon footprint, everything involved in training. It really helps democratize access to high-performance AI.
Absolutely. And to put some numbers on it, the Phi-Mamba model hit an average score of 65.1 across those benchmarks. The hybrid Phi-Mamba versions also did exceptionally well, especially compared to other attention Mamba hybrids around the 1.5 billion parameter mark trained conventionally. What's really striking is they often achieve this using fewer attention layers and fewer overall parameters than those conventionally trained counterparts. It's a real testament to how effectively MOHAWK transfers knowledge. It's not just shrinking a model, it's making it smarter with existing knowledge, so it needs fewer parameters to do the job well. That's huge for deployment and research iteration speed.
And digging into those hybrid architectures, Table 4 in the paper explored how best to combine attention and Mamba layers, right? What did they find?
Yeah, they tried different setups, attention just at the start, just at the end, or spread throughout. And the consistent finding was that interleaving Mamba 2 layers uniformly with attention layers, so mixing them evenly throughout the network, gave the best performance on the downstream benchmarks. This aligns with findings in other models too, like Samba, suggesting there might be a broader principle here about synergy. A truly integrated hybrid, where both mechanisms contribute throughout, seems more effective than keeping them segregated in different parts of the network.
Interesting. So a true blend works best.
It seems so. And again, underpinning all these results was that rigorous experimental setup we touched on. Extensive grid searches for hyperparameters for each stage, using robust tools like AtomW, weight decay, gradient clipping, the WSD scheduler. This meticulous optimization ensures the reported results aren't just lucky accidents, but come from a carefully designed, stable, and effective framework. It shows the engineering work that complements the theoretical insights.
Okay, as we wrap up this deep dive on MOHAWK, let's try and connect it back to the bigger picture of our Beyond Transformer series. Where does this fit in the evolving landscape of AI, especially regarding SSMs and transformers?
Well, what's really fascinating is how MOHAWK leverages that concept of structured state space duality, SSD, which underpins Mamba 2 and Hydra. Remember, SSD shows that SSMs inherently have both these linear recurrent forms, great for efficient compression, and quadratic attention-like forms capable of more global interactions. They're fundamentally tied to those semi-separable matrices, which provide this mathematical bridge. MOHAWK brilliantly exploits this deep shared structure between SSMs and transformers. It's not just finding a superficial resemblance, it's tapping into a fundamental mathematical kinship. It kind of suggests that maybe these architectures, despite looking different, are actually closer cousins than we thought, representing information in fundamentally compatible ways.
And that compatibility allows this effective knowledge transfer, which then ties into that crucial distinction about data types.
Exactly. Transformers thrive on pre-processed, tokenized data. They need the raw input cleaned up and chunked. But SSMs, with their compression bias and recurrent nature, excel at processing raw, fine-grained stuff directly characters, audio waveforms, DNA. MOHAWK's ability to distill transformer knowledge into SSMs means we can potentially combine the best of both worlds. The sophisticated high-level understanding from pre-trained transformers with the raw data processing power of SSMs. Imagine an AI that understands speech directly from sound waves or biology from raw gene sequences without needing that intermediate tokenization step.
Which leads us towards that grand vision of tokenizer-free AI.
Precisely. That's one of the exciting frontiers. Models like HNets, which we'll cover in our next deep dive, already show how SSM layers, specifically Mamba 2, boost performance when operating directly on raw data. They leverage that a strong inductive bias for compression. And interestingly, HNets trained end-to-end show remarkable robustness to things like typos or phrasing variations, things that often trip up tokenized models. This suggests learning from finer-grained raw data might lead to more fundamentally robust understanding.
So MOHAWK isn't the final destination, but it's a really crucial bridge.
I think that's a great way to put it. It lets us leverage the enormous investment we've already made in training huge transformers, all that embedded knowledge. But it simultaneously helps us move towards these more foundational, potentially more robust tokenizer-free systems that can interact directly with the raw messiness of the real world. It's smart reuse combined with forward progress.
Okay, we've reached the end of another deep dive, and what a fascinating look at the MOHAWK framework. Just to recap, MOHAWK offers this really sophisticated, multi-stage approach that skillfully bridges the gap between powerful but compute-heavy transformers and efficient subquadratic SSMs. It's a clever way to reuse the immense intelligence captured in existing pre-trained models, making high performance more accessible and efficient.
And the value proposition for you, the listener, is pretty clear. This enables the creation of smaller, faster AI models that still achieve remarkable performance. It pushes the boundaries of what's feasible with limited resources, speeding up research, development, and ultimately deployment of advanced AI in more places. It's a very pragmatic and powerful step forward.
And that leaves us with, perhaps, a final provocative thought for you to consider. If we can successfully distill complex intelligence across such fundamentally different architectures, transforming knowledge from a database model to a streaming brain model, what does that imply about the nature of knowledge or intelligence itself within these networks? Does it point towards some deeper universal principles of information processing, regardless of the specific nuts and bolts? And looking ahead, what frontiers might this open for truly integrated multimodal AI systems? Systems that learn directly from diverse raw data streams, unconstrained by artificial processing steps, and perhaps becoming inherently more robust and adaptable as a result. Lots to think about. Keep exploring, and we'll continue our deep dive into the next generation of sequence and language modeling next time.